So we're studying moist air, psychrometrics. Remember, moist air, as we model it, is always an ideal gas mixture. Always an ideal gas mixture. It's made up of dry air as a single entity with a molar mass of 28.97, as well as water vapor. Water vapor with a molar mass 18.02. The water vapor behaves as an ideal gas in that moist air mixture. Somebody says, justify the assumption that water vapor in saturated air at 30 degrees C behaves as an ideal gas. How would you justify it? Well, you would say, I know how to model vapor. And I would think about using the tables, the steam tables. And in the steam tables, I think about properties. I think about pressure, temperature, specific volume, internal energy, enthalpy, entropy, right? And then I think about what's it mean to model that as an ideal gas. Well, there's a relationship between some of the properties for an ideal gas. It's an equation. The ideal gas equation's P, V is equal to RT. So it's like this same pressure here shows up here, this same temperature here shows up here, and this same specific volume here shows up there. They also talk about, but it's not the critical point, for an ideal gas, U is a function of temperature only and H is a function of temperature only. But if I really wanted to justify that I can treat water vapor as an ideal gas, what I could do is I could compute the specific volume using the ideal gas equation, which is RT over P. So given T and given P, compute V, the specific volume for water vapor, assuming ideal gas equation applies. Also, I say, let's go and get it out of the tables. V out of the tables given temperature and pressure. Okay. So what pressure would I give it? I would give it the partial pressure that the vapor exerts in that moist air. Here, maybe I could go and get the Psat at 30 degrees C. That would be my PV because it's saturated air, 100% relative humidity. So I would look this up in the table. I would compute this. Do you think those two values will be the same to 18 digits? No. Not even 9 digits. Not even 7 digits. But they're going to be close. Hopefully close. And that was, so we would compare them. We'd say, well, what's the difference between the value out of the table and the value computed using the ideal gas equation for the specific volume? Water vapor. And we would normalize it maybe by the table value. Maybe we just are interested in not plus or minus like positive or negative, but just get the absolute value of that. And that's a measure of error. And if that difference is, let's say, less than 1%, I'm feeling good. Less than 0.01%, I'm feeling really happy. It's a good approximation. True? So what we've done is we calculated it, this error, absolute value of the specific volume using the benchmark, using the tables, using the steam properties calculated typically in software which are used to produce the tables. And then the ideal gas equation, and you normalize it by comparing it to the table value. Okay. We plot on a temperature, specific volume, a TV diagram. TV diagram. Notice that this V is not on a linear scale, but a log scale. So this is 10 to the minus 3. This is 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2. And 10 to the 3. So that's a large range of specific volumes, is it not? Now, we don't have many applications in the very high temperature range, but you could still check to see if the ideal gas equation is approximately good. We would never want to use it under the dome. Never. So don't even compute an error under the dome. It's just out in the vapor region. So what we have is we plotted a number of lines at constant pressure, like 100 kilopascal, 1 megapascal, and then we plot lines of constant error. This is a line of constant error of 0.1%. That's a very small error, 0.1%. That's this error plotted. And notice that all the way down to saturated vapor, around 2 kilopascal, is very small error. Okay? And then this is a line of constant error going up. So if I said the point in right here, that's even less than 0.1% error, because it's probably on some value that slopes like that. And maybe up here, it's even less error. So everything to the right of that curve is less than 0.1% error. Here's a line of 0.25% error and 0.5% error. Can you see that? So what's remarkable is that even saturated vapor at low pressures behaves as an ideal gas. You don't have to be very far from the dome. You just don't, you can't or shouldn't be up near the critical point. You're getting some significant errors. This is 10% error. Engineer doesn't like that large of a percent error, right? So as long as you're down, let's say, in the 0.5% or less, it's a very good approximation.
We're looking at 30 degrees Celsius.
Yeah, and so if you looked at 30 degrees C, that would be right in here. And you're looking at saturated, it would be right in here. So you're looking at less than 0.2, around 0.2% error visually. Very small error. Good approximation. Last time we talked about the air balances. We talked about water balances. The challenge with the water balance is some of the water can either go liquid to vapor or vapor to liquid, true? This is condensing, and this is boiling or evaporating. Okay, humidifying or dehumidifying the moist air. But then we talked about the energy balance equation. And there you have all the tools. You're equipped with all the tools to model and do energy balances for moist air problems. And we stepped into one last time, did we not? Started one, did we not? But I think the best thing to do is just solve a problem. So let's solve this problem. So we have air at 12 degrees C and 30 meters cubed per minute. That's a volumetric flow rate, and 30% relative humidity. It's being heated and humidified. How do you heat it? You pass it over a hot surface. It becomes hot. But that hot surface does not add water. It will not humidify it. How do you humidify air? Spray in water. You could spray in liquid water, or you could spray in steam, or it's two-phase quality, some hot water, cold water, but you just spray in water. Okay. It exits at a given temperature and relative humidity. So make a little sketch of the system. Here's my box where things are happening. It's being heated and humidified in this box. So it comes in at state 1, goes out at state 2, and we just list information. Temperature 1 is 12 degrees C. The volumetric flow rate at 1 is 30 meters cubed per minute, and the relative humidity at 1 is 30%. It's heated, so I can think about a hot coil as well as humidified. Maybe I throw in some liquid water or some water. I'm throwing in some steam, some water. It comes out at a temperature of 32 degrees C. It's a lot warmer, and the relative humidity of 40%. Liquid water is supplied at 25 degrees C to the humidifier, so there it is. It's the mass flow rate of liquid water, and it's at 25 degrees C. That's what's coming in. The pressure is 1.3 kilopascal throughout, so it's constant pressure everywhere. The pressure is not changing. What is the mass flow rate of dry air entering the coil in kilograms per minute? Well, if I'm asked to calculate the mass flow rate of dry air, would it not be the volumetric flow rate at 1 times the mass density, or 1 over the specific volume of dry air at 1? Is that good? Okay. So how do I calculate, let's say, the specific volume of dry air at 1? Is it R bar T divided by the pressure of the dry air at 1? The temperature at 1? Okay. If I use this equation, I need that in... Yeah, you need the molar mass of the dry air. Thank you very much. The absolute temperature, 273, add 12, 285 Kelvin. Okay. And what about the partial pressure of the dry air at 1? Well, that's going to be the total pressure minus the vapor pressure at 1. They told me the relative humidity, so the partial pressure at 1 is the relative humidity at 1 times the saturation pressure at the 12 degrees C. Okay? So I take a look and I see that the saturation pressure is 1.402 kilopascal multiplied by the 30%, and I get that this is 0.4206 kilopascal, which then allows me to calculate 100.88 kilopascal for the dry air pressure. And then it allows me to calculate the density. Actually, I calculated 1 over that. I calculated the density of dry air, 1.2334 kilograms of dry air per meter cubed. Then multiplied by the volumetric flow rate, and I calculated the mass flow rate of the dry air to be right at 37.0 kilograms of dry air per minute. So that's the answer to the first part of the problem. What is the flow rate of liquid water supplied to the humidifier? Well, water balance. And so I'm asked to calculate m dot liquid. It's going to be the mass flow rate of the dry air times the difference in humidity ratio. So it comes in at low but goes out high humidity ratio, omega 1 and omega 2. So at this point I need to calculate omega 1. How do I calculate humidity ratio at state 1? Yep, 0.622 PV1 over PDA1. That's exactly right. Okay. And when you calculate that, you find that it's 0.002593 kilograms of water per kilogram of dry air. Then we have to do a little work about this one. So I get the saturation pressure at 32 degrees C out of the tables, 4.759 kilopascal. I multiply that by the relative humidity to get the vapor pressure at the exit. That comes in at 1.9036 kilopascal. I then get the omega 2, 0.622 times PV2 divided by P total minus PV2. Same equation, and then we calculate that omega 2, 0.01191. Notice that it's larger. It's omega, the outlet humidity ratio is greater than the inlet humidity ratio. Makes sense. You're humidifying, amount of water vapor goes up per kilogram of dry air. So then we stick into this equation, we get the mass flow rate of the liquid. They want it in kilograms per minute, 0.345 kilograms per minute. It's not a lot, is it? You got to wait a whole minute, and you don't even get half of a kilogram. You get a third, roughly, of a kilogram. Make sense? of liquid water.
The mass flow rate, or like that goes out.
Yeah.
Given, am I right? Or should we calculate? Oh, we should.
Yeah.
Because it was confusing about the M dot for dry air.
Yeah, that's what goes in and goes out. 37 goes through the system. 37 kilograms per minute of dry air. So.
I just found that saturation, that pressure,
Uh-huh.
at 12 degrees Celsius, it's 1.4 kilopascal.
Did I write it down wrong?
Sir,
At which temperature?
12 degrees Celsius?
At 12? Yeah, 1.402, and then I multiply by 30%, 0.3. Yeah. Look good? Any other comments on this? Okay.
I just have a question. That MDA, that was the mass flow rate of the dry air. That was from AB times rho.
Yeah, times rho of the dry air at the inlet. Yeah, because you reciprocate rho over 1 over rho. All right? All right. Now the last question is the harder one. What's the rate of heat transfer to the moist air? But you're equipped with all the tools. Just go slow. Okay? So think of 3 streams flowing through this. You have the dry air flows in and out. You have some vapor that flows from here to there. True? And then what you have is some liquid that flows from here to there. But it comes in liquid, it goes out vapor. So those are the 3 fluid streams to help break down and do the energy balance. Okay? So let's do this. Let's write an energy balance for a little control volume where you have moist air in, liquid water in, and moist air out. Okay? So we would say something like the rate at which heat is being added. Let's draw it that way. So this is Q dot into the control volume. That rate at which heat is being added is equal to the mass flow rate of the dry air. It comes out at higher enthalpy than it went in for the dry air. The mass flow rate of the vapor that comes in, that's kind of just going through the system. It goes out at higher than in for the vapor. And then I never leave enough room. I'm sorry, I need to scoot this over just, oops. I need to try and scoot this over just a little bit. All right. Plus the mass flow rate of the liquid comes in and it goes out as vapor at 2. I'm going to write H of G at 2. But how did it come in? Liquid, H of F at the liquid, H of F at 25 degrees C. Right? This H of G, it goes out at 32 degrees C. So we're going to evaluate H of F at 25 and H of G at 32. Make sense? Yeah. Yeah. Now, so let's 3 mass flows, exactly right. When we come back up here, we have a mass balance equation. I'm just going to rewrite it. The mass flow rate of the liquid is equal to the mass flow rate of the vapor out minus the mass flow rate of the vapor in. Is that true from water balance?
Yes.
That makes sense? So I'm going to replace it right here. Okay? And then what I'm going to do is divide the whole equation. Well, I don't need to do that. But I could, well, just take m dot dry air out of every term. So if I pull it out of every term, I'll have the specific heat of dry air times the outlet temperature minus the inlet temperature of dry air. Then I'm going to have the humidity ratio coming in. times h of g going out at 32 degrees minus h of g coming in at 12. True? The vapor came in at 12, out at 32. Okay. And then this term, I know it's a couple steps here, but I'm running out of room. This is going to be the mass of the vapor 2 minus the mass of the vapor 1. But if I divide by the mass flow rate of dry air, mass flow rate of dry air, then that's simply omega 2 minus omega 1. So it's going to be omega 2 minus omega 1 times h of g at 32 minus h of f at 25. I got to scoot down a little bit, 25. And then I close that bracket because the mass flow rate of dry air multiplies all of that. It's one way of writing it. Okay? It's one way of writing it. So what we find is that the first term, which is the sensible heating of the dry air, okay? Let me scoot down a little more. That first term, the sensible heating of the dry air, is 12.4 kilowatts. Okay. What about this second term, multiplying by the red dot, mass flow rate of dry air? But maybe I should give you the value so you can look it up. The h of g at 12, what is that? 25, 23.4. The h of g at 32, 25, 59.9. Okay. We already have omega 1 and mass flow rate. So what is this? This is the sensible heating of the vapor that already is in the moist air coming through. But you know what? That only requires 0.06 kilowatts. The next one, though, is it's mainly due to the vaporization of the liquid that comes in, but it's vaporized at 25, but then it's heated a little bit from 25 to 32, but it's primarily the latent heating of that liquid. What do you mean by latent? Well, it's an old term, but still used out there. Sensible. If I add some heat, the temperature changes. Latent means hidden, and if I add some heat, the temperature doesn't change. So it's like hidden heat. Well, why didn't the temperature change? Because it was going into changing the phase, going from liquid to vapor. So anytime you have phase change, they talk about, oh, that's a latent heat component.
So the liquid that you added in just vaporized?
It vaporized, and then there's still a little bit of sensible heat because it vaporized at 25, and then from 25 to 32. But I'm going to just lump it and call it all a latent. Yeah. Okay. But what the point is this comes in right at a whopping 14.4 kilowatts. So when I add them up, I get the total load is 26.6 kilowatts. That's what's needed. The heater needs to provide it. And 53% of that heat went basically to vaporize the liquid water. And only 0.2%, a negligible amount, went to heat the vapor that was already in the airstream. But a large percent, 47%, did go to heating the air. And believe me, out there in practice, this is one of those things that if you're ever in the MEP field, you're ever doing air conditioning in South Texas and all that, they want to bust it out, and the people want to double check that you've accounted for both the sensible load on that coil as well as the latent load. You wouldn't believe how many times I get asked questions like that. Okay? Can you double check these calculations? Somebody's insinuating I forgot the latent load, or claiming I didn't account for it in my design. Okay? So that's what they mean. There's a lot of energy that has to be supplied or removed to a coil. Supplied to a heating coil if you're having to vaporize, removed from using the coil if you're condensing. Okay? Makes sense? Very good. So I forgot to box it, but there's our final answer for the last part. So we're done with that problem. So make sure you're able to solve problems where you have evaporation, that's like heating, and humidification, just like we did, as well as cooling and condensation, a cooling coil. Flow over a heating coil, flow over a cooling coil. Got it? Okay. Let's talk about something very practical. You know, we're equipped with information in this class that you can go out now and explain things in your own mind and maybe to people that you interact with about why things happen the way they happen. So some of us have some experience with air compressors. You ever seen one? You ever owned one? You ever operated one? You ever had to take care of one? Well, get the manual out of this little pancake air compressor. A lot of times they'll have a tank. This is just a little, 2.5 gallon, 5 gallon pancake type tank. Okay? A lot of them have big tanks, large tanks. Okay? This is where you can pick it up and carry it. But they have a storage tank. So what it does is it dumps in high pressure, now hot because it went through the compressor, air. Now where did it get that air from? It got it from the surrounding air. That air had some humidity in it. And now that water does something funny. At first, when it dumps it into the tank, it's hot air. But you let that air sit overnight or just a couple hours, it's cooling, it gets to the same temperature as the room. But it's at high pressure. You can take the tools in this class, and we'll do that, and show that it cannot hold as much moisture. So even though the air out here may be 50% relative humidity, when you pressurize it, put it in a tank, it's hot, that's fine, it's not going to have a problem with humidity then. But if you let it sit in a tank and cool under high pressure, it will become saturated air. It'll be some of that water vapor will condense. And it's mind-boggling. I still remember, like, what? Where did that water come from? How come I got water in this tank? Liquid water in this tank. How did I get liquid water in the tank? It came from the surrounding humidity. The air brought it in. Okay, so if you take a look at your table of contents when you purchase one of these, you can often find some safety instructions. So I turn to that page to show you. They have a lot of don't do this, don't do that. But look down here. Drain tank daily. Drain tank daily or after use. The internal rust causes tank failure and explosion. So, I mean, there you go. And so here's an illustration. And right here on number 8, that's the drain valve. Look at, here's 8. Here is the drain valve. It's sticking off. So you can just go down there, untwist it, keep it unplugged. And then if it's still got some pressure in it, it'll really shoot it out. If you tilt it a little bit to make sure that's the lowest spot, the gravity will make the water go over the surface of that plug, and you'll get some rust-colored, junk shot out water. If it's high pressure, it will spray all over. And if you have pants and other shirts, it'll make it all kind of that reddish. You've done it. I've done it. Many times. Who else has done that? Yeah, okay. See, this class equips you to understand what's going on in your life, right? So I thought I'll make up a problem that'll illustrate this phenomenon. So here's the problem. I start with moist air that's fairly warm, 45 degrees C. It's at high pressure. It's just been shoved into the tank. And it has the humidity ratio, which is the ratio of how much water vapor there is per kilogram of dry air. That was in a lot of outdoor air that gets ingested into these devices, 0.01 humidity ratio. I was going to say percent, but it's just 0.01. That's a humidity ratio of a lot of outdoor air. It fluctuates as the temperature and the humidity changes. So if you're over in Houston, you're going to have more challenges with water in your compressed air system. If you're in El Paso, you have less challenges. True? That's true. That's right. That's right. A lot of times in these compressed air systems, they'll have dryers and filters before that air gets to their tool. And if they don't, Well,
Those two though.
yeah, some tools can accommodate water vapor, but some tools can't. And if you're in a paint spray shop and you use air, you don't want any water going into your paint gun, right? You want it dry. So you'll have a very high efficiency filter and desiccant to keep it dry. But anyway, I thought what we'd do is we would cool it at constant pressure to a final temperature of 25 degrees C.
Is that ambient?
Yeah, ambient temperature, back to ambient. So I know we set up this little illustration of a piston in a cylinder. This is idealized of what's going on. And we set it up a little time later, and the piston's constant weight, it maintains the constant pressure of 400 kilopascal. So this P1 is equal to P2 is equal to 400 kilopascal. This is state 1. This is state 2. It starts off at T1 hot, 45 degrees C. It ends up T2 of 25 degrees C. It starts off with humidity ratio, omega, of 0.01. Okay? It's cooled, so what we're asked to find is that heat transfer in kilojoules per kilogram of dry air. Kilogram of dry air. So it's like I'm asked to calculate Q per M of dA, or lowercase q. Well, my system is the trapped moist air. True? Here it is at a later time after it's been cooled. What's interesting, though, is I suspect there will be a little blue puddle. Some of that humidity will have condensed. And I suspect that it will be 100% relative humidity. And I need to account for that in the Q. Otherwise, my calculation will be wrong. If I don't account for that, I've omitted or failed to account for the latent heat associated with the condensing of some of that vapor. Okay. So I say, how am I going to calculate this Q? Well, just write the first law. Let's say it's Q, and I'm going to, do you want to stay with the traditional sign convention, or you want to abandon it? Either one. You got to pick one. Either you get on this road or you get on that road. We know it's Q out, but if this is my system and I put Q in, traditional sign convention, I'm going to calculate a negative answer. Do we want to calculate a negative answer? Is that the route we want to go?
Yes.
Let's stay with it. So my first law would be something like this. U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. Kind of a generic first law, neglecting changes in kinetic potential energy. It's for a process from initial state 1 to final state 2. True? Constant pressure. I can take that, express it, integral PdV, it's boundary work, and shove it over there. I have no shaft work. It's just boundary work. So I get that Q1 to 2 is equal to H2 minus H1. You were equipped with all of the resources, tools, and analysis skills to do that step long before this class. True or false? True. You understand that. So now all we have to say is, I have a change in enthalpy. Okay, we'll bust it into two components. Let's consider the mass of dry air that's trapped in the system. And it's going to end at enthalpy 2 and start at enthalpy 1 of the dry air. And we're going to have the mass that's a vapor. But you know, I'm going to bust that mass and the vapor into two things, because after the end of the process, I expect there's some liquid. So I'll have the mass of the vapor to begin with, state 1, V1. But at the end, it's equal to the mass of the vapor that's in the vapor state, plus the mass that may have condensed is now liquid at the bottom of the tank. Does that mass balance for water make sense? So I'm just going to say the mass, that's the vapor, that is ending in the vapor, times, it starts with H of G, it ends of H of G at 2 minus H of G at 1, and then I still didn't leave enough room, did I? I always have to move this over. I don't know why I don't leave enough room there. Plus the mass that's now in the liquid at 2, it ends H of F at 2, and it begins H of G at 1. these two enthalpies are precisely the same. It's H of G at 45 degrees C, H of G at 45 degrees C. It's just some of it ended as liquid, H of F, at 25 C. Some of it ended as vapor at 25 degrees C. That makes sense? That equation look good? Very good. All right. This Q, they wanted the answer in, so I divide over by M of dry air. If I divide everything by the mass of dry air, 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 true? Then I see this is my lowercase q that I'm asked to calculate. This is just C sub P, T final minus T initial for the dry air. This is omega 2, the final humidity ratio, times the H of G2 minus H of G1. And this one now, it depends how pretty you want these things to look, okay? This mass of liquid final is equal to the mass of vapor initial minus the mass of vapor final, true? If I divide by the mass of dry air, the mass of dry air, the mass of dry air, that's simply going to be omega 1 minus omega 2 times H of F at 2 minus H of G at 1. Did you follow that little sleight of hand, that little trick right there? That little, yeah, I'm a magician. That's what some students think. I'm a magician up here. That make sense?
Yes.
Okay, so now there's another sleight of hand that I can do as well. What I can do is I can do this. I can say H of F at 2 minus H of G at 1. I can say minus H of F at 1 plus H of F at 1. This is H of F at 1. No, that's not what I wanted to do. Let me do this. This is not the sleight of hand I wanted. Okay, H of F of 2 minus H of G of 1. I brought down these two terms, that one and that one. And then I do this. I put minus H of G of 2 plus H of G of 2. So I added nothing to them. True? Okay, but this group I want to leave because that's minus H of FG, true, at 2. And this group right here is the same as that group right there. So Q is equal to C sub P T2 minus T1 for the dry air, plus I'll have the omega 2 times H of G of 2. Now I regret doing that. I should have stuck with it. Times the omega plus omega 1 minus omega 2 times H of G minus H of G1. And then I still have down here omega 1 minus omega 2 times minus H of FG at 2. What did that really buy me? Not much. Well, what it does is it cancels this omega 2. This term cancels with this term. So you're left with Q is equal to C sub P T2 minus T1 plus omega 1 times H of G2 minus H of G1 plus omega 1 minus omega 2 times H of, with a minus H of FG at 2. Okay, let's substitute some numbers. So it's 1.005. What is that temperature difference for this problem? It goes from 45 down to 25, so that's minus 20. True? Plus omega 1, which I know you can calculate. Well, no, it was 0.01. Omega 1 is 0.01. H of G at 2, 25, 47.2 minus H of G at 1, 25, 83.2. Plus and then omega 1 minus omega 2. I calculate omega 2. It's in your skill set. You find that omega 2 is 0.0022. Now I know that these numbers are hard to see, but it's like 0.00100. See, that's 4 digits. This is 4 digits, okay? So it's like 100% went to 22% and 78%. So what's 22%? 22% of the vapor that was in there stays vapor, but 78% of it turns to liquid. Okay? So this number, omega 1 minus omega 2, is 0.0078 times the minus HFG, which is the negative 2442.3. Did I do that right? I think I did it right. Meaning that you calculate that it's negative 20.1 kilojoules per kilogram dry air for sensible cooling of the dry air, negative 0.36 kilojoules per kilogram of dry air for sensible cooling of the vapor, and negative 19.05 kilojoules per kilogram dry air for the latent, for the condensation of 78% of the initial vapor in the tank. So you get a total Q of negative 39.5 kilojoules per kilogram dry air. Again, you can look at these percentages. This is around 48%. This is a 0.9%, right under 1%, and this is about 51%. So a lot of the heat transfer is associated with condensing that vapor. Half of it, 48% is. But you can see now, if I started put that hot air with that humidity ratio in a tank, I just let it cool, I'm going to get a liquid in the bottom. Quite a bit of that vapor will become liquid. In this calculation, 78% was liquid. Thank you very much for your attention.